Hi everyone. Here I have a transmit array unit cell. Okay, I call it a transmit array because there is no reflecting plane here. I only have one slab of dielectric and one metallic part here. Very simple. And what I want to show you in this video is like, what are these S parameters and then how they relate to linear polarization and circular polarization. I've seen these questions on the comment section of my videos, and I thought, okay, instead of trying to reply with like minimum space, I can make a video. Okay, so here you can see that this slab is on a square lattice. Okay, and we have W, the size is about 30 millimeter. So if you think of it, usually the unit cell should be smaller than lambda over 2, right? So it would be sub-wavelength for a transmit array or reflect array, right? And then it might be even smaller than that. So what we want to look at when the size is about 30 millimeter, that means that the higher frequency is about 60 millimeter, which is going to be 500 megahertz, 5 gigahertz, and then lower than that, right? So I might have made a mistake in the middle of that, but let's see about this. It doesn't matter, the frequency response doesn't matter, okay? This is like a dummy unit cell. What I want to explain is the concept of linear polarization and circular polarization when you excited this unit cell with two Fluctuate ports, and on each Fluctuate port you have TE and TM polarization. TE is basically vector A, which is in X direction, and then B is vector B, which is along Y direction, which is going to be your TM. So you have to remember this, okay? Because when we simulate this thing, I simulated it, I think already. Let me see that. When you simulate it, what you're going to get is not in terms of TE and TM. What you're going to get is numbers. So let's go here. So these are S parameters. I'm going to translate these S parameters that you would see here, okay? So here it says look at port 1, then colon 1. That means from port 1 in the first direction, which was our X direction, which is our TE mode, okay? So TE mode in port 1 to TE mode in port 1. So this is basically reflection coefficient for TE, okay? So if you want to translate it into terms that we would know, it's basically S11 TE TE. This one, what is the meaning of this one? Let's practice. Port 1, mode 2. So port 1 TM to port 1 TE, the first one. So this is reflection coefficient from TE to TM on the first port. So this is like a cross polarization, cross linear polarization, TE to TM at the first port. Let's go down. Let's look at this one. This looks complicated. Port 2, polarization 1. So port 2, TE, port 1, TM. So it says from port 2, TE, we are going to port 1, TM. So that's a transmission coefficient because the port number changed, transmission coefficient, but from TE to TM. So that's what? Cross polarization again, right? Now, if you want to know if your unit cell is circularly polarized or linearly polarized, we're going to look at the spectrum or the answers of reflection coefficients or transmission coefficients for TE and TM separately, and then look at this. Look at how they relate to each other, and then translate that to circular polarization. Okay. There are papers on this. I will comment one of them. I will put the paper, my paper actually, where I explain how you can get the circular polarization coefficients based on the linear polarization. which is TM and TM, TE and TM. Okay, so what we need right now, this is a transmit array, so I'm gonna look at the transmission coefficients. And then you always go, do not confuse yourself. You always go from TE to TE or TM to TM. Okay, so first transmission coefficients. So we have to go from 2 to 1, but 1 to 1 as well. So 2 to 1, 1 to 1. This is the number of the port has changed. So this is the transmission coefficient in direction of TE. Both of them are TE. So this is 1. This is S21 TE TE. Again, transmission coefficient. Then we want another one, which is transmission coefficient TM TM. And then here, I'm gonna draw the magnitude, plot the magnitude, which is in dB. And then, or let's try the raw magnitude actually. That would be better, magnitude. So I'm going to change this. So I'm gonna say apply trace. And then we are going to look at their phases too. So if I'm not mistaken, it's gonna be Cang. Because Cang is one of them wraps it, the other one doesn't wrap it. So you can just do that as well. Okay. So let's look at this. You see, I simulated this from 5 to 15 gigahertz, and I want to know where is circularly polarized, where it is linearly polarized. Okay. So let's look at this one actually. This area below, I don't know, this is probably 500, 5.5, 6, and then here, yeah, I don't know the frequencies. I should do it good division. So if it was in dB, let's change it again. 2, 1, and then the other one was this one. I'm going to plot them in dB so you can see that. Yeah, for the explanation. Here you can see that nothing in this polarization, everything in this polarization is going to pass up to, let's say, here, right? And in the other polarization, it doesn't pass. So here, this is the frequency we're going to look at. 5.7, the transmission coefficient of TE mode, 2 to 1, 1 TE. So transmission coefficient of TE between 5.7 gigahertz and then 5.2 is below 10 dB. That's when the slab that we put, it's going to resonate, and it's going to, if I'm not wrong, let's see. This is actually in Y direction. That's interesting. Why is it resonating in that direction? Okay, that's for you to answer actually. You can see that maybe I got the directions wrong, but anyway, one transmission coefficient in TE mode, it's completely below 10 dB, which means no transmission. On the other hand, the other one is very close to 0 dB, which is like full transmission. So in this area, this unit cell is fully linearly polarized in one direction, which is our TM1 in Y direction or TM direction. Now, the other one, now let's look at if they are ever, if this becomes a circularly polarized, okay? It's a little bit easier to look at it here in the magnitude perspective, in the magnitude absolute value, because dB is like, they get super close. Okay. Maybe actually, it's actually quite hard to design a circularly polarized unit cell, otherwise everybody would do it. But let's see, like you can see here, like you have to have phase difference of 90 dB, okay? So you can see here, if usually the trick is you make one of these directions non-resonant and the other one resonant. Then you would have a very narrow band circularly polarized wave, right? For example, here you can see if this is non-resonant, this is a non-resonant response, right? The green one, which is our TM, non-resonant constant, right? And then the other one resonances in TE, and then you see a flip in the phase, which is from -90 to plus. No, no, actually, I have a feeling that this is like, if I did it with, maybe if I do this 201, it would become better. Let's see. Yeah, like, yeah, it should be from -90 to +90. So always remember resonance of 1, it's going to be -90. So here, this difference is 70. Here is like about, yeah. Here it gets to 90, but this doesn't matter because the magnitudes are so different, right? Remember? Then, yeah, this doesn't become a circularly polarized unit cell because it's quite actually hard. But imagine, right? Imagine right at 5.5, let's say, 5 point, yeah. If the magnitudes were the same, then the magnitudes were the same and the phases were like this much different, like about 90, like here, if you add these two, you're going to get exactly 90, M3 and M2, you see? The difference is exactly 90. Then at this frequency, it would become a perfect circularly polarized. But right now, yeah, the magnitudes are so different here. We have to go lower in frequency, I feel like. Lower or higher? Oh, yeah, I bet there is something going on here. That's why the other, I don't think I got to the resonance of this TM mode yet. This is about 20 millimeter. You can measure it. So let's go to E and then edge. And then you can here say measure edge. So this is about 20 millimeter, okay? 20 millimeter. The resonant frequency, if this is lambda over 2, right? Lambda over 2, lambda must be 40 millimeter. So 40 millimeter, then 300 over 40, that's about 7.5 gigahertz. It should have become, what am I missing here? Maybe because of, yeah, let's go lower in frequency. I don't know why. Like 2, then above 10, that would be just higher order modes. So don't ignore those. Then we're gonna solve this again. Oh, actually, no, it's not gonna solve it again because I didn't change this. So I'm gonna change this to 5. I'm trying to see if I can find a frequency where this is like becomes a circularly polarized one, which it wouldn't. You would need, yeah, you would. It would be very high actually. No, actually, you like it would be very high frequency if it ever become a circularly polarized one, unless I do this. I add some in X direction. I add some bits too. So let's say 25, and this becomes like, I don't know, at 15, apply. Something like this might become circularly polarized in the frequency that we want. So, here, say this is good, this is good. Okay, I'm gonna clean this. Let's see what's the differences right now. Because yeah, in the other direction, it would be so in the other direction, it would be so small that it would only resonate in very high frequencies. And you kind of wanted both of them to resonate, but then one after the other. That's how the trick is to the circular polarization. So here I'm getting somewhere, guys. I'm getting somewhere. Okay, so let's do deletion. And then now we can see if this would work. Okay, so I simulated this again and let's look at this. Let's see if this ever would work. Yeah, this is like they're meeting here, but I'm not sure if their phase difference would be, let's see. It would be a very bad circularly polarized one if it works. So M1, 7.96. Let's see. It's not easy, guys. It's not easy to design. What are the degrees? Why is it like this? Okay, so M4, 796, M4, we have to go lower. One more. Okay, not bad. Okay, not bad. Like about 100 something. But you know how you can define? You can define an equation, okay? How did I used to do that? You can define equations, and then when you do that, then it becomes easy. Calculator, was it calculator? I think so. Oh yeah, here. Okay. No, this is for the fields. I know something. Yeah, guys, wait. There's somewhere that you can define. Oh, here. Nice. Okay, so let's call this T LHCP and then the other one RHCP, for example. Okay, so here what we're gonna do, we're gonna grab those. This is a very much more complicated equation that depends on the cross polarizations too. Okay, but simply let's say we have S211, which is this one. Okay, we're gonna put the magnitude of it. Um, circular polarization is half of this plus half of this plus multiplied this, which we're going to insert. How did we used to do that? Insert into expression? No, sorry. I completely forgot how we did used to do this. Okay, maybe I have to use something. Half multiplied by, then you can say real of this. Oh, here. Real of this plus imaginary of it, which is 1j. I don't know what would happen if I just put, let's do it easy. Let's say you don't want to put anything, none. Insert into expression plus 1j multiplied by the Tm, which is like transmission coefficient Te plus j Tm. And then if you had the 90-degree difference, then they would either add up for LHCP or they would cancel each other for RHCP, for example. Okay, so let's do the other one. Do you see it, guys? It's this one. So I'm gonna insert this one in here and then close it. Okay, TLHCP, I'm gonna add this and then I'm gonna bring it here and I'm gonna call it RHCP and then minus and then add this one again too and then done. Okay, now what I'm going to do is going to plot output variables TRHCP, TLHCP, both of them in the B20, I think. Let's see. So you see like here, like here at this frequency, you have TRHCP, you see, it's very close to actually 7.98, right? When you have one of them cancel the other one, because almost the phase difference between them was about 106 or something. So yeah, you see, like, because of the cross polarizations and stuff, here you can see almost, if we could get this level, like this is about minus 4.6 dB, right? If we could bring this up to 0 and then have the TE and TM modes meet their magnitudes to meet in like magnitude of 1, and then this would be a perfect circular polarization, okay? If now it's almost like this is like a TLHCP and this is TRHCP, so you have one circular polarization, which is much more than the other one, right? And again, these are very simple equations for LHCP and RHCP. You have to add the cross polarizations too. I'll put the, actually, I can copy the paper, my paper there at the description, so you can just refer to that, because both in transmission and then in reflection cases, it tells you what these formulas have to be, so you can just create equations just like I did and then have them plotted. But in order for you to understand what you're doing beside the equations, is that when you design a circular polarized way unit cell, what you're trying to do is to find a frequency, or at the desired frequency that you want, to meet their magnitudes desirably around 1, not 58. 1 they would meet, and then they have about 90-degree phase difference. Okay, I hope you learned something from this video, and like, subscribe, and share. Thank you.